So without any late, I request Dr. D. Apparao Garu to give brief introduction about Dr. Mogula Gopinath Garu, who is going to present his topic in the next session. Thank you. Over to you, Apparao sir.
Okay, Dr. Santosh sir, thank you for. Am I audible, sir?
Yes, sir. Yes,
Hello?
sir. Go ahead.
Okay. Okay. Myself, Dr. D. Appara, Assistant Professor, Department of Mechanical Engineering, Aditya Institute of Technology and Management, TKL. First of all, I would like to say thanks to Dr. P. Srihari Garu, Professor and HOD, Department of Mechanical Engineering, and also coordinator of this ATAL FDP, for providing this opportunity to introduce today's resource person. It's my pleasure to introduce today's resource person, Dr. Mogula Gopinath Garu, for our ATAL Faculty Development Program. Dr. Mogula Gopinath Garu earned his BE in Mechanical Production and Industrial Engineering from Geetham College of Engineering from 2004 to 2007, and he did his masters in laser material processing from IIT Kharagpur from 2011 to 2013. During his masters at IIT Kharagpur, Dr. Gopinath Garu completed significant projects including online monitoring of pre-placed powder laser cladding in 2012. This project focused on the use of laser cladding techniques in and to enhance material processing by integrating real-time monitoring for improved quality and efficiency in manufacturing. Dr. Gopinath Garu completed another key project during his masters at IIT Kharagpur is the surface hardening of titanium alloy during turning via pyrolytic carbonization. This project focused on enhancing the surface hardness of titanium alloy by employing pyrolytic carbonization during the turning process, improving its wear resistance and performance. He pursued his PhD at IIT Kharagpur, where his research focused on advanced material processing techniques, including laser and solid state welding, particularly in additive manufacturing and laser material processing. Dr. Gopinath Garu completed his PhD from IIT Kharagpur in 2018, after which he worked as a senior scientific officer for 1 year. In April 2019, he joined IIT Hyderabad as an assistant professor in the Department of Mechanical and Aerospace Engineering, where he continues to focus on his research in advanced manufacturing process, including advanced manufacturing, laser material processing, and solid state welding. At a relatively younger age, he has 46 Scopus indexed journals and articles, out of which majority of the SAI Q1 and Q2 with an impressive H index of 19. Now I request Dr. Gopinath Garu to start his session.
Thank you, Dr. Apparao Garu. Thank you very much for the nice introduction. So just I'm trying to share my screen. I hope my screen is visible.
Yes, sir.
Yeah.
Yes, sir.
Yeah. Thank you very much for the nice introduction. And once again, I thank the entire institute for inviting me for this talk. Okay. So today I will be trying to, introduce you to some complexities what we face in additive manufacturing process. As every one of you know, additive manufacturing is something which is extending the manufacturability limits. So today when we ask anyone why additive manufacturing, because if you talk about manufacturing processes, there are n number of manufacturing processes. Then why only what we call this additive manufacturing? So one of the main reason, technical reason. So of course, people say it can generate complex components, but you have to understand the basic design principle is the design should be as simple as possible, meeting all the requirements or the functionality. A design should never be complex. But why are we making complex? To improve the efficiency and other aspects. So a simple statement of improving the complexity or increasing the complexity is not the major one. But what it does is it improves what we call it as manufacturability. Okay. So one thing which additive manufacturing is little bit advanced compared to the other other conventional manufacturing processes is manufacturability. Now, what do you mean by manufacturability? If you can see the component over here, which is kind of an impeller blade, that kind of an impeller blade can be directly fabricated from a CAD model with a slicing data and other aspects. But the more important thing is, yes, If you want to do this in machining, it will take a lot of effort and what we call it as buy to fly ratio. Typically, if you are doing the machining again of these kind of components, impellers, then essentially you will be taking an ingot. From the ingot, you will be removing the material. And once the material is removed, then you will get the more or less this kind of a form. And if you look at the surfaces, all the surfaces are curved. So essentially it requires a kind of 5-axis CNC. And your tool should be able to access these zones, which are difficult to reach. So that makes or that creates a limit called as manufacturability limit, which additive manufacturing to a greater extent can overcome. Of course, the way we look at additive manufacturing over internet is very different, where you will see a lot of complex components were fabricated out of that. That's true, but there is years of effort behind that to realize one single component. Now, I will try to address some of them, because whether you talk about bio, whether you talk about mechanical components, or whether you talk about 4D printing, the essential idea or the ingredient is the process. Process remains the same. Your application is different. So we will first try to look from the process perspective, and we will try to understand the basics of the process. Once you understand the process, you will be able to generate any kind of component as per your need and necessity. So now let us try to understand how this process works. Of course, again, additive manufacturing process or additive manufacturing is very wide. Within additive manufacturing process, you have a lot of them. The first one, we call it as powder bed fusion process, which is very popular. Most of you might have heard. The other one is DED, directed energy deposition process. Then you have extrusion based additive manufacturing process, which we typically call it as FDM, typical 3D printers. Then you have VAT polymerization, which is your SLA printers. And you have binder jetting, material jetting, and so on. So if you see, and then ultrasonic joining or ultrasonic or stack additive manufacturing kind of thing, or laminated object manufacturing, LOM, LOM. Okay. So these are the 7 manufacturing processes which ASTM identifies as additive manufacturing process. Now, if you ask me, are these only 7? No, there are several of them today. But as per ASTM, this is the categorized, or it categorizes additive manufacturing into 7. Out of that, we will be looking at one of the important process, that is DED. But again, in DED, you can use, when you talk about DED, you can use laser beam as an energy source. Yes. Okay. You can use laser as energy source. You can use electron beam as an energy source. And then you can also use arc, electric arc, okay, as an energy source. Now, depending upon which source you are using as in for heating or melting the material, it has its own capabilities, limitations, advantages. Okay. But today, essentially, considering the time and other aspects, we will keep our focus mainly on the directed energy deposition process, where our idea is to look into where laser is used. Now, by definition, all of you know this particular process, the simultaneously material is fed and melted and deposited. Okay. So what happens in an LDED process, which first we will try to understand that will, and then the moment I show you the components that we build using this process, you will be able to appreciate how this process is really useful in manufacturing process. Okay. Now you look at this schematic. All that you have is a nozzle. It's like almost like 2 conical nozzles with different diameters inserted one into the other, which forms this annular channel through which you will be sending your metal powders. Okay. So these metal powders, once comes out of the nozzle, they will start interacting with your laser beam. Now, not just that, there is also the other background story that, you know, the moment it interacts with the laser beam, they don't really melt. Rather, the laser beam will partially get absorbed in these powder particles, and the subsequent one or the subsequent or the remaining energy will reach to the substrate. It melts your substrate, and these powder particles will go and drop into that molten pool. And once these heated powder particles get into the molten pool, they melt there and then. And then as the laser beam moves in this direction, whatever is the molten pool formed because of the laser on the substrate plus powder which entered will form into a bead. And then you have something called as overlapping tracks. Overlapping tracks, if you are using, it is typically can be called as a cladding process, laser cladding process. Combined with overlapping layers will result in additive manufacturing. Now, what do you mean by overlapping and overlaying? Just for your understanding, what happens in additive manufacturing? First, you will deposit one bead, and to cover an entire surface, what you will do? You will keep overlapping the single beads. And below this, what you have is your substrate. Okay, this is your substrate. Now, if you stop this process at this point, we call it as laser cladding, which is a surface engineering technique for improving the surface properties. Now, instead of stopping there, if you keep depositing, then what you have overlapping tracks plus overlapping or overlaying. Okay, it is overlaying layers. So a combination of these two will give you something called as layer by layer manufacturing or additive manufacturing, or you can call generative manufacturing also. Now, in reality, how does this process look like? Simple. You have a coaxial nozzle. Typically, we call this one as a coaxial nozzle. So, from the nozzle, what is coming out is the powder. Who is carrying that powder is your carrier gas, what you can see over here. So now if you see, the one interesting thing about this powder that is coming out of the nozzle, it's just flowing like water. Not just that, you look at this location. Here, the powder stream actually converges. So the moment the powder stream converges, that tells you that your nozzle is in a very nice condition or the nozzle design is good. Yes, nozzle design itself has a science in it. Otherwise, what happens the moment the powder comes out of the nozzle, it will just get diverged. But that is not going to happen. Rather, what it will happen is it will focus. The nozzle design will be such, it will focus. Once the powder stream that is coming out of nozzle is stabilized, then you will put on your laser on. The moment laser is switched on, what will happen? Now, this is in a this particular video was taken in such a condition that the powder particles are illuminated using LED lights. So that's why, and it's a monochromatic video. But if you look at a color video, this is how it looks like. You won't be able to see the powder particles, but whatever you are seeing here is actually the laser material interaction zone. So this is what we call it as laser material interaction zone. Now what is happening here? Most of the energy or some of the energy is getting into the particles such that they are getting heated up. You can see these powder particles heated up or spreading out. And whatever is remaining after getting absorbed is actually going into what you call substrate. Now, once the process is set nicely, this is what you are going to see in reality. If you look with your own eyes, this is how it looks like. Okay, just give me a minute. So now you can see it is actually doing one layer first, and then it will go by certain height. Just a minute. So it will increase, keep on increasing its height, right? Now, if you look at in a larger scale, now what you are seeing here in the previous slides is at a fundamental level. Okay. Now, if you look at what we call it at industry level or at component level, this is how the process typically looks like. So you can obviously see over here the kind of component we are trying to fabricate. This is at IIT Hyderabad. And a component of any size or more or less simple shape can be made. And not just that, I mean, like one thing which we have to also understand is the surface quality. When we talk about implants or when we talk about mechanical components, you look at any mechanical component in and around you. You take a simple bolt and nut around you, right? If you look at that bolt and nut, its surface quality is extremely good. Yes, Dr. Satyanarayan Reddy, you had some question?
Yeah.
Yes.
How about the oxidation, sir? Yeah. Are you doing here?
Yes. So typically, if you look at here in this, from this nozzle, there will be three gases coming out. One, we call it as carrier gas. The carrier gas is typically, again, it is actually carrying the metal powder to the processing zone, which is argon. And then you have something called as shielding gas, which is again an argon, which prevents the metal fumes coming out of the molten pool entering into the nozzle. Then you have something called as shaping gas, which does not allow the powder stream to diverge. Now, if you see, all of these are argon. So this argon gas forms a shielding over the molten pool.
I got it, sir. Thank you.
Okay, so that is important. Now, again, coming back to our discussion, one important aspect or one of the disadvantage or drawback of this additive manufacturing process is its surface quality. I mean, like when you take a additively manufactured components, if it is made out of SLA process, stereolithography process, typically the surfaces are relatively smooth. But if you are talking about metallic components, then the surfaces are not as smooth as you get in the conventional manufacturing process. So always, or if you look at a proper textbook, additive manufacturing is defined as a near net shaping process. Okay, what do you mean by near net shaping process? It will give the component a shape near to the final one, but it is not the final one. So first we have to understand that. Okay, and that's the reason today we actually go with more or less like a hybrid approach. What do you mean by hybrid approach? We integrate our additive manufacturing systems with subtractive systems. I will show you one system in the subsequent slide where you will appreciate how we do this. So if you look at this, you look at this component, right? This is almost this is 30 centimeter in width and 440 centimeter in height. Okay, so currently our research is more focused on large area additive manufacturing process. That's how we are looking at making components for rocket nozzles and some other components which are of aerospace interest. So that's the reason our components typically what we build are of larger scale. Of course, the fundamental science or the fundamental mechanical property analysis happens at a Cooper level like 100 mm by 100 mm by 100 mm samples. Other than that, the components. So essential idea is one important aspect which everyone has to understand is post additive manufacturing. Some kind of post processing is required. And today we are looking at more or less systems with combination of both of them. Okay. Now, this is what the system which we developed looks like, because like I said, we are looking at bigger components like rocket fuel tanks, rocket fuel engines. Now, if you look at this system, which we have developed with the help of funding from DRDO, we named it as Large Area Additive Manufacturing System, LAM. Okay. Now, you look at this system and you can see there are people over here, right, working on that. Now, this particular system can build a component of the order of 2 meters in diameter and 3 meters in height. You can just imagine what kind of component we are talking about. And if you look at carefully this system once again, see over here, there is a robotic arm. Now, what is this robotic arm doing over here? Essentially, post deposition of few layers or few layers of material or few, once you build a certain height, this entire system will move up because it has its own guides. And then this robotic arm will get activated. and this robotic arm moves inside and it does the machining whatever is required the way we have shown over here. Okay, this machining is going on with the robotic arm. So that way, the idea is to balance the surface quality, because once the entire component is built of the order of 3 meters, you won't be able to do any machining on it because it's too huge to handle. So the idea here is go in a phased manner, you deposit up to a certain height, then you machine it. Now, why do you think this machining is required? You look at your hip implants, or you look at any other implant today we are talking about. One important aspect of any implant is surface quality, and like someone asked it now, the oxidation. If it oxidizes, then it is no more biocompatible. Not always. Okay. So oxidation is sometimes not good, and it may lead to it may so happen that it will no more be biocompatible. Now, all those aspects have to be controlled, which includes surface finish as one of the parameters. And yes, people do surface texturing for the better growth of the tissue on the implant, but that is a controlled texture. But what you get as a surface quality here is a kind of uncontrolled and unpredictable surface. Because, like I said, if you have a molten pool, the powder particles come and sit on the molten pool at the wedge of its solidification. So if you look at any additive manufacturing surface, if this is the layer that is additively manufactured, on the surface of that you will see partially assimilated or partially fused powder particles, which sometimes can be also get removed if you are applying little bit of amount of pressure. And just imagine you bake an implant out of that and it goes into body. Okay, and it is same true with the powder bed fusion process also, because typically when we talk about implants, they are made out of what you call this powder bed fusion process. But when you talk about coatings on an implant, that is sometimes made out of DED, sometimes made out of plasma spray coating. So always the interfaces. Yes, someone had some question. Hello, someone has a question? Fine.
No, sir.
Yeah.
Hello, good day, sir.
Yeah.
Sir, is the machine is this one is the metallic based of additive manufacturing or general with the like your fiber metal or any
No. This is purely metal.
metal. So then, in this cases, just I want a small suggestion. The hexagonal in between as a hexagonal body-like structure, right, sir?
Okay.
Or packaging we are using in that in between that the inset of the metal, right?
Okay.
In the hexagonal is the outer edge. Then in between that one metal line, if you'll put, can it be possible to this machine?
Can you repeat your question?
Just like in hexagonal body-like structure. Okay. Suppose
Okay.
for any gadgets we for packaging purpose we will use. Okay.
Okay.
Or for any vehicle or any for any substance for outer side body, we will
Yes.
want to lightweight. You want to just to reduce the weight of that particular one. Okay?
Yes.
So at that moment, to strengthen, we are using a certain metal inside it. Okay.
Okay.
So can this one be possible through this type of machines?
So are you trying to say that already an existing component in between you want to keep something?
What is the main component for filling? As in filler material as well as the boundary materials for this machine.
Okay. So typically here we use metal powders. Okay.
Okay.
So it can make you kind of lattice structure if you want. It can make, but not as much as, because typically if you are talking about lightweighting aspects, we try to see again that lightweighting in our opinion has two phases of it. All high strength materials falls under the category of lightweighting, plus typically aluminum alloys, which are low dense materials, also fall under lightweighting. And then you talk about the exotic structures. Yes, that will be able, we will be able to fabricate on these things.
Because now research is going on that area. So
yes,
how the body will be in the light manner, and generally hexagonal we are choosing to provide the better strength on that case.
Oh, you were talking about honeycomb then?
Exactly, honeycomb based system.
I understood. Yes, that can be made. So see, typically honeycomb for us gives a different kind of what you call advantage, that it takes the impact also in addition to lightweighting and other things. For lightweighting, we use a lot of other structures, but
Yes,
honeycomb, acoustic wise, it is good. And then,
and strength wise also good. It is found.
Exactly. Yes,
Exactly.
true. We can make it. We have several of them.
Hmm.
Okay. Yeah. So
Right. Thank you, sir.
now you look at this particular component. Just it's not like boosting, but this is the largest metal component printed on DED in India. Okay. So you can see this is almost like 1 meter. And this is almost like 1.2 meters. So this entire component is built by additive manufacturing using this DED process and using this DED printer what we have developed in-house here. And you can see the kind of accuracy. You look at this particular edge, how sharp it is. Now, this typically did not happen over a month or so. There were years of effort to reach to this state. Now, the idea here is, yes, most of the times we see this kind of components in literature or in kind of internet database. But today our essential idea is, because most of us are researchers or we are in academics, so we need to know more about the process rather than what magics it can do, right? So that's where my presentation would be morely focusing on the process physics. But the essential background why I'm giving is to show the capability of additive manufacturing. Today, there are extreme domains. Few people are talking about nano and micro fabrication of micro pillars for antennas and other aspects. We are on the extreme side where we are looking at large scale additive manufacturing. And in between, there are people who are looking from the biocompatible materials, implants, and all aspects. But the process is more or less similar. So that is what I am going to address today. Now, first thing which we have encountered when we looked at deposition of this component, or you will encounter looking at any kind of component, is something called as waviness. Now, you look at the component what we are trying to show you over here. It's a very small component. It's not a very big one. But essentially, if you see, as the deposition process is continuing, you will observe one interesting thing. That is, this particular guide, whichever is getting deposited, is actually started accumulating the heat. Now, you may think, how is this important? It is important in two aspects. One, if you talk about what you say mechanical property, if you talk about surface property, is a function of its microstructure, what we call it as T curves, time temperature transformation curves. Now, if you look at this time temperature transformation curve, the microstructure essentially is dictated by how the material is cooling. It is equally important for surface properties, which may be wear resistance, which may be hardness, which may be scratch resistance, which may be biocompatibility, because the microstructure controls all of them, including the corrosion. And again, the corrosion can be any kind of environment, including the body fluids. Now, all of them, when we say, is controlled by microstructure. And unfortunately, your process, the thermal cycle, the first layer is undergoing, and the thermal cycle, the last layer is undergoing, is not the same. And across the layers, the kind of thermal gradient we are looking at is extremely different, which essentially means the microstructure over here, over here, over here, over here, over here is expected to be different. Not just that, when you talk about stability, process stability, it depends also upon whether you are giving exactly the amount of heat required or you are giving additional heat. Now, why am I worried about it? Now, assume that you look at the cross section of this particular wall. How does it look like? The cross section of this wall will be looking like something like this. There is a bead 1, bead 2, bead 3. Yes, Vamsi, you had some question? Hello? Okay. So now, if you look at these beads, these are continuously building like this. This is what our expectation is. But what is the reality? The reality will be something like this. The first bead will be okay. The second bead will also be more or less okay because it is able to dissipate the heat. From certain number of beads onward, since it starts accumulating the heat, the molten pool will become unstable, as well as because there is an additional energy available because of what you call this heat accumulation effect. This molten pool size becomes bigger. At one point of time, it becomes unstable when it falls down. Right? This is what we call it as tear effect. So your cross section will look like this. So what is your expectation? Your expectation is that my cross section should look like this. But what you have ended up is a cross section like this. We call it as teardrop effect. And what is the reason? The very first layer that you are depositing on the substrate has your substrate, which will act as a heat sink. Your substrate is a heat sink. So immediately the entire heat is absorbed. So it solidifies very quickly. Because we are talking about a molten pool, it solidifies very quickly. Now, subsequent to deposition of few more tracks, now what has happened? One, because of the previous depositions, the temperature of the substrate will increase, right? And earlier, the deposited track was immediately able to dissipate the heat. But now it has to dissipate the heat from the top to through the heated wall into the substrate. Now, if you see, the delta T is very high here. What is this delta T? The thermal gradient. So it cools fast. So your cooling rate is fast. Now, if your cooling rate is fast, you can say microstructure is refined. But now, what happens to this layer where you are depositing? Already the previously deposited layers are heated up and they are at an elevated temperature, and substrate has got continuously the heat from the previously deposited layer. Then the delta T will drop. Okay, so the temperature gradient will drop, or the temperature of the substrate will go high. The temperature of the previously deposited layers will go high, all leading to the decrease in delta T. Therefore, your molten pool size will become bigger, making your entire deposition non-uniform. Now, not just that, even when you are doing cladding also, the same thing will happen, because when you deposit the first track, heat went into the substrate. Second track, again heat went into. So by the time you come to the last track, your height will keep on increasing and you will have a non-uniform height of coating, which is very popular in additive manufacturing. Now, one way of resolving it is, after each pass or after each track, wait for some time, which we call it as interpass delay. Technically, give an interpass delay, and during that interpass delay, your substrate will cool down. It will come to the initial state and you deposit the next layer. By doing so, you will be able to control it. But is it acceptable to industry is a bigger question, because for industry, it looks at what are the number of components that I can produce per day, per month, per year. Now, if you introduce something called as interpass delay into the process, then the productivity will come down. That is, number of components produced per day will come down. The moment so this is not acceptable for the industry. Now, considering these facts, people have tried out several things. Many interesting things, actually, to say. So one is they are doing forced convective cooling. They use typically the fans, what you have in your computers, SMPS fans. They try to force the air to cool the molten pool or the substrate, what we call it as forced convection technique. And again, in this, there are something called as active cooling, passive cooling. Passive cooling means below the substrate, you give another big block of copper. Copper being highly thermally conductive, it will try to absorb the heat from the substrate. But it is called as passive cooling, because over a period of time, this will also get heated up. There is an active cooling system. What is an active cooling system? You still give the copper, but try to flow water through the copper substrate. So it will have an internal channel through which water is flowing, and it will continuously dissipate the heat because it is connected to a chiller. This is what we call it as active cooling. Of course, people have done without this passive and active cooling. They have used fins or fans and tried to cool it. Of course, there are extreme steps or extreme methods where this entirely deposited component will keep on entering into the water, so that whatever is deposited, that always stays at room temperature or the temperature of the water. So as the component increases, you keep filling it with the water. But only thing is, we also have to be very careful about hydrogen embrittlement or the reactivity of the component with the water, because it's at high temperature. So all those aspects also have to be well considered. Right now, if you see this one slide, which is a collection of literature, except that video, there are a lot of methods that are reported in literature. But the problem is, none of these can be adopted in industry, because industry will not be happy to dip their component inside the water, and putting off this active cooling or fans is not acceptable, because if you are using powder as the feedstock material, it will create its own issues. And substrate, okay, fine, if you use active cooling up to this height, it may be able to solve the issue, but what happens beyond that is not in control again. So this is where what we did is we looked into alternative methods, what we call it as monitoring methods. Okay, today we talk about more about sustainable manufacturing. You talk about more efficient manufacturing process, or you talk about industry 4.0. What are all these things looking at? All these things look at, can you make your manufacturing process smart? What do you mean by smart again? I mean, like industry 4.0 has a number of definitions to it. But for us, when you talk about smart manufacturing process, in your process of deposition or machining, cutting, welding, anything, you have some kind of sensors which try to take the data out of it, and this data carries the signature of the process, signature of the defects, signature of the anomalies. That is what we call it as smart manufacturing process. Now, if you consider this, the immediate, our idea was, okay, let us try to quantify this heat accumulation and also qualitatively see how this heat accumulation looks like. So that is what you are seeing over in this slide. If you see, the deposition is happening, and we kept a sensor called as IR pyrometer. Pyrometer is essentially a non-contact type temperature measurement device that works on the IR radiation emitted by any body. A best example during the COVID time, or even today, even in what we call this hospitals, especially these pediatric hospitals, people are using this thermometer, a non-contact type thermometer. It's an IR thermometer. Just they will focus at your body based on the IR radiation your body is emitting. They will tell what is the temperature of your body, and no more you require that contact type of mercury thermometer. Okay, that is not required, because today everything is non-contact. Right now, the same principle here, we are using an IR pyrometer to understand the temperature. Now, if you see, one is visually you are able to see that heat is getting accumulated, the component is becoming red hot. Right. The other thing from the sensor, what you can see is this one is the thermal cycle for the first layer. You can see, when I say thermal cycle, it is a time temperature history, time and temperature history, where the material gets heated up. It will cross its T, let us say solidus. It will cross its T liquidus, and then once the laser moves out, it will try to cool down, and then there will be a slope of change, and again it will cool down. This is what we call it as a thermal cycle. Now, if you see, especially post heating, the duration is nothing but your cooling time. And you can always, from the cooling time, you can always quantify what is the kind of heat accumulation. If it is cooling slow, then there is a lot of heat accumulation. If it is cooling fast, there is no heat accumulation. So that kind of data you are getting from this particular signal. Now, if you see after that, let us say 20th layer, the temperature is no more dropping to the minimum detectable temperature of the pyrometer, because before the next layer is being deposited, the temperature of your previously deposited layer is still at 1050. So it is pretty hot, and the next layer is coming on. Now, this is something which is problematic, especially in DED process. In powder bed fusion process, this problem is relatively controlled. The very much reason is, in powder bed fusion, first the stage 1, okay, is spreading the metal powder on the base plate. First you will spread a layer of powder on the base plate, then the laser will come and scan those required locations, okay, and it will try to melt it. And then again the step is, again a fresh layer of powder is spread, and again the laser scans. Now if you see, before 2 scans, there is one intermediate step where you are trying to spread the powder. That acts as an interpass delay, which will try to reduce the effect of heat accumulation. But such kind of things are not there in DED, essentially because of which you will encounter something called as waviness. This is the first problem you will encounter in additive manufacturing. You assume that you have a CAD model. Idea was to generate that CAD model, but what you will end up with is, because of heat accumulation, you will end up with this kind of an waviness. Now we will try to see how to essentially address this waviness and how to control this waviness. The very much reason I'm stressing on this aspect is because it is a process physics. If the process physics is understood, all that you need to do is generate a CAD model, take the STL data, feed it to the machine, it will deposit, provided your parameters are tuned to take care of these effects. Otherwise, again, you will have a CAD model, you will have a deposition, but there is no matching between these two. It's a kind of thing which regularly we see in additive manufacturing process. Now, the essential idea is, now you have to make your process smart enough such that it will control this waviness on its own. Now, how do we do it? The idea essentially, again, this shows our experimental setup, again, a lab scale experimental setup. This is your, what we call it as DED head. Just give me 1 minute. I just need to take some water. Just a minute. Yeah, sorry. So if you see over here, you have a DED head. There are 2 IR pyrometers over here. This is the IR pyrometer 1. This is the IR pyrometer 2, which are non-contact type. One is essentially keeps monitoring what is the substrate temperature just below the deposition, and the other one will move in that direction so that as the layer height is increasing, this height will also increase so that it will take the temperature from the current layer. That is how it works. And then you can also see, in addition to that, we are also using this active cooling, because whatever is feasible, you have to apply. So if you see here, this is a copper block, and you can see there are a lot of water pipes. And so this is inlet, and if you see, the outlet is somewhere in between. The idea here is the sequence in which the water flows in this block is also very important. What do you mean by that? Assume that this is your top view of this actively cooling channel. If the water enters like this, goes like this in a uniform way, by the time it comes here, it may be at 90 degrees. Let us say it is at 90 degrees. It is entering at 18 degrees. So within this, there is a gradient of, let us say this is 20. There is a 70-degree gradient. So that is something which is not acceptable to us. Rather, we try to homogenize it. How? Again, you will make the water enter here, right? It exits, it goes somewhere here, it exits, it comes somewhere here, it exits, it comes here, exits, it comes here. So this way, what we are trying to do, this kind of gradients we are killing. So that is why, if you see, yes, Sirinaidu, yeah, have some doubt?
No, sir. Sorry, sir. No, sir.
Okay, no issue,
Continue,
no
sir,
issue.
please.
Yeah. So now if you see, at every state, there is some process physics that is going into this particular deposition or additive manufacturing. Same is the case with your powder bed fusion process, where you try to preheat the bed for a different region. Okay. But here we are trying to cool the bed for a different region. But the process physics, there is some process physics involved in it. And if you see, at every step and every stage, the minute details have to be taken care such that your deposition is coming good. Now, essentially what we have done is, this was in an open loop. Open loop means essentially we are trying to look at it and we are trying to modify the parameters from our side. Now, if you see, cycle number 1, 2, 3, 4, 5, 6, 7, 8. 8 layers are deposited, and in all the cases you can see the temperature is dropping down to the minimum detectable temperature of the pyrometer. So you need not stop the process, keep continuing it. But after you see here, now we have started observing that, okay, the temperature is not reaching to the minimum detectable temperature of the pyrometer. The moment we look at this kind of things, then what we will try to do is, one, you reduce the Q heat input, right? Now, what is the line energy? Line energy is an amount of energy supplied per unit length, that is laser power divided by scanning speed. Okay. Now, a line energy can be reduced by reducing the laser power or increasing the scanning speed. That way, you will be able to reduce the input energy. The moment you do that, so whatever is the Q coming out of heat accumulation, right, is balanced by reducing the Q by certain value. Okay. Now, if you say Q reduced plus QHA will be actually equal to the Q, that is initial heat input, whatever you are giving. So this way, if you can look at the process, if you can manipulate what you call these input parameters from this kind of a deposition, where you can see there is a lot of waviness, right, which is not acceptable. From there, you can come to a deposition like this, where you will not see any kind of, what you say, waviness. Now, what if you see, hardly we looked into 4 slides, but there are a lot of systems, sensors integrated into the process such that we were able to generate this kind of data and this kind of finished uniform balls. Yes, it takes over a year or so to come to this stage where you will be able to address these kind of aspects. But the essential idea is you are looking at a process in a holistic view, where you have a lot of sensors integrated, making the process smart, which will allow you to get lots and lots of data. Of course, this data can be utilized to look into the geometrical aspects, control the geometrical aspects. Not just that, you will be able to predict the microstructure that is going to be present in this particular deposition, because microstructure again is a function of cooling rate, time, temperature, transformation curves. That is where we are coming from. So it will tell you about which kind of microstructure, what kind of grain structure, refined, coarse, and subsequently you will also understand what will be its effect on the mechanical properties. If you see, one sensor is talking about geometry, it's talking about what you call temperature gradients, coolants, controlling the geometry, and then it is also talking about the microstructure, which subsequently correlates with the mechanical properties. So it's kind of an end-to-end solution which talks about the entire, cycle of this additive manufacturing process. So that makes this manufacturing process a little bit smart in terms of adding the sensors. So that is what I'm trying to show here. So the essential idea or takeaway, at least in this kind of a short-term course, I understand that, you know, the absorption rate is less because a lot of things were taught in a very short period of time and for a longer duration. So there is a fatigue involved in it. But the takeaway from this slide, whatever we have discussed till now, is in additive manufacturing, what we see in YouTube and other internet sources is not actually the, I mean, like the way we imagine that it will make anything is not true. There are certain problems. One of them is the heat accumulation problem, which results in inhomogeneous microstructure, leads to anisotropy in the mechanical properties, also affects the geometrical tolerances. So now one way of controlling it is making your process smart or industry 4.0 ready, because the reason why I am avoiding industry 4.0 is a time bound. Tomorrow industry 5.0 comes, 7.0, 6.0, it keeps on evolving. But all of them fall under the category of what we so-called smart manufacturing, where you integrate the sensors. So the idea is you have to understand there is a heat accumulation effect and you need to control it. And why it happens is the important aspect which you have tried to cover till now. Yes, Dr. Satyanarayan Reddy.
Yes, sir. Actually, like, you know, there's a water-cooled copper chill block which you use in the direction certification.
Yes.
Castings. So here also, if you incorporate the water-cooled chill block and
Yes.
vary the flow of water so that the heat removal,
Yes.
whenever you want, you can increase or decrease by varying the water flow rate. That might. Do you think that might help to some extent, sir?
No, because the problem is in investment casting, if you see, so it's if you look at investment casting, it is also a near net shaping process. Additive manufacturing is a near net shaping process. But the only problem is additive manufacturing is a top-down approach. So layer after layer is coming. So where will you keep your cooling channels? So except at the bottom of the substrate, nowhere else you can keep these chills or cooling channels. Whereas in your investment casting, you know there is a defined cavity in which the entire molten pool is going to come and sit. And then you can use these cooling channels in and around to cool it effectively. Or if you want directional solidification and etc., at some locations you can keep extracting the heat at a rapid pace so that the grains will start moving towards that, or the grains will start moving from that position towards the high temperature. That kind of thing in additive manufacturing is tough. All that you can do is give the heating at the bottom of the plate, except that you can't give anywhere else. That is a limitation.
Okay, sir. Okay, thank you.
Now, one thing is, even after you take care of all these things, one important aspect which we should not forget is in additive manufacturing, whether it is powder bed fusion process or laser directed energy deposition process, if you are using 1 kilo of powder, your component will weigh only 300 grams or 400 or 500 grams, which essentially means I'm talking about the catchment efficiency. Catchment efficiency means what is the quantity of powder that is coming out of the nozzle, what is the quantity of powder that is getting deposited, right? If you look at this ratio, that is ratio of the material deposited to the ratio of the material dispensed, typically you will end up with 30 to 50% catchment efficiency. Now, where is this remaining 50% is going? It just falls in and around this deposited component. But the important point is this powder is now exposed to the open atmosphere, right? And sometimes it might be contaminated. Not just that, because of other issues also, there can be some kind of oxidation. And one thing which you have to understand is oxidation is an uncontrolled phenomena, especially in this process. So because of this oxidation, is it an endothermic reaction or exothermic reaction? That we have to again answer. Definitely, oxidation is an exothermic reaction, so it will add additional heat into the process. The moment additional heat comes into the process, then again the molten pool size will become bigger, making it unstable, and then you will have the onset of waviness again. Now remember, we are talking about onset of waviness due to heat accumulation. Parallelly, we are talking about the process anomalies, which can be oxidation of the powder or contaminated powder or oxidation of the deposited layer. Anything can add additional heat and create some waviness. For that, if you want to address that, the whatever understanding till now we have developed is not sufficient. You have to look more deeper into the process. That is what we will be discussing in the next slide. Now, whatever we have seen previously is all kind of regular, what you say, cameras. What cameras? DSLR cameras, whatever we typically use at homes. But now what you are looking at is a slow speed monochromatic camera or high speed monochromatic camera. And the most important thing which we need to look into in this video is powder particles are coming in, good. But parallelly, you can see a lot of powder particles are going out, right? So there is something called as laser material interaction. That is, some energy is going into the powder, some energy is going into the substrate, creating the molten pool. Powder particles are going and falling out of into them, and some are flying away. So this is how all the three videos till now we looked into. One is the slow speed, high speed camera. The other one is the regular DSLR camera. The other one is the not monochromatic. It's just in normal mode. Now the essential idea here is you have to understand again what is happening in this deposition process. What happens in this deposition process essentially is there is a powder cloud, right? Because you are dispensing the powder, and through this powder cloud your laser beam is passing through. So wherever the laser beam falls on this powder cloud, the powder particles gets heated up. Now whatever is the laser that can pass through the powder cloud will actually reach to the substrate. Fine. That laser which is passing through this powder cloud, reaching the substrate, will actually create the molten pool into which these heated powder particles come and deposit. Now, if you see, there is one important aspect here. Now we have to have a question in our mind. That is, what is the fraction that can go into the powder? What is the fraction that it should reach to the substrate? Is there a limit on it? Right? Can all the energy go into the powder particles, or can all the energy go into the substrate will actually dictate what is the kind of bead quality or the bead geometry you are getting in this additive manufacturing process. That to a greater extent will control and dictate whether you are able to make a component which you require. Assume that you are making a component with a lot of porosity. It doesn't make any sense because aesthetically it may look good, right? If you look at your hip bone implant design, right? One, it has to have enough strength to take a human body load, right? And the surface should be smooth enough and biocompatible. So all this comes from what is happening in this particular process. Now, considering those aspects, again, if you go back into any one of the videos where we are showing the deposition, yeah. Now, if you see between the nozzle and the substrate, there is some amount of distance. This is what we call it as standoff distance. And there is a very significant effect of this standoff distance. What is it? Just a minute. Yeah. Now, this is an halo. The powder is coming from the halo cone. Now, if you keep the substrate, now assume that this is the powder coming out of the nozzle. Then there is a powder focal point. You can say powder focal point. And above that, or this is the powder converging zone, powder converging zone, powder diverging zone. Now, what happens if you keep your substrate here? That is the case what we are talking about here. What happens? Because since the powder is coming out of the coaxial nozzle, the entire laser energy will interact with the substrate. Now, what happens if I keep my substrate here? There can be a good apportionment between the powder particles and the substrate. Now, what happens if I keep my substrate here? From here, over this entire length, the powder is interacting with the laser beam and it will start extracting most of that energy. Now the amount of energy reaching the substrate will reduce. Now the question arises here is, you need to know what is the energy that is reaching to the substrate, what is the energy that is reaching to the powder. Now one way of doing in an experimental way, because we are more experimentalists. So what we look at is, we will allow the laser and powder to interact over a length. Okay, interact over a length where you are supposed to keep the substrate. Now, instead of substrate, you will keep a gas jet. Allow the powder to interact with the laser till that point where your substrate is supposed to be kept. And instead of substrate, you keep a air jacket or a nozzle through which the gas is flowing. So this will take away the powder particles from this material interaction zone. Then what will happen? Definitely using the gas jet, you won't be able to deflect the laser beam. No. So the laser beam will now pass on to the power meter, which was kept just below the laser beam. So now it will tell us what is the energy that is absorbed in the powder particles, what is the remaining energy that is reaching to the substrate. Now, in reality, how the experimental setup looks like, this is how it looks like. You can see the laser is coming from the center of the nozzle, the powder is coming through the nozzle, they are allowed to interact over a length, and after that, we have just kept a gas jet. And the rest of the energy goes and falls onto the power meter, giving you an understanding or the estimate of what is the energy reaching substrate. Now, what is its implication? Its implication is very simple and clear from the single bit studies, where you can see when you are keeping your substrate above the powder focal point, you can see the laser beam is directly interacting with the substrate. Now, what will happen? Since the laser beam is directly interacting with the substrate, you will observe that your substrate or the previously deposited layer will melt excessively. Whereas, if you look at what is the deposition, you had very small amount of deposition. Now the question is, is it good? Okay, we will answer it later. Now, when you keep the distance as 20 mm, that is the powder focal point on the substrate, then you will see there is a decent amount of melting of your substrate or previously deposited layer. Followed by that, you have the deposition. This is the deposited area. Now, this is good, definitely. This is acting as a metallurgical bonding. It is establishing a metallurgical bonding. And parallelly, you have a deposition. Now, what I'm trying to do subsequently is further increase it to 25 mm. Means more of an energy is going into the powder particles. Then if you see, yes, I got a good deposition, agreed. But if you look at the amount of melt of the substrate is very less. Now what will happen to this is, when you keep depositing the multiple layers, because of the thermal stresses being generated in this process, this guy will delaminate actually. And then the entire component will come out of the substrate. That is a kind of danger you will have. Now, is this good? Is this good? That we haven't answered. Which one of them are good? Yes, this is definitely good for additive manufacturing, right? But what about this one? And what about this one? That is what we will try to see a little bit, because that will tell you, how to control the entire process. Right? The same thing over again in a different kind of version and the view what I'm trying to show. You can see 15 mm distance, the laser material interaction zone is less, energy went into the substrate, higher melt. 20 mm, the laser material interaction zone is slightly higher, so lesser amount of energy went into the substrate, more went into the deposition. If you further increase to 25 mm, then again much more lesser came into the substrate, so the amount of bonding is less, which may or may not be sufficient. But again, is this good? Is this good? Is this good? Is not answered. This is definitely good for additive manufacturing. That much I can tell you. Now again, the question pops out one more time, which one is good? Now, the idea over here is, okay, one figure is missing. Now, assume that the top layer is having a waviness like this. Okay, I'm taking one crust and one trough for an easy understanding of the process. Now, I will set my standoff distance in such a way that the nozzle distance or the distance between the nozzle tip and this deposition is 15 mm over here, and it will be 20 or 25 mm over here, 20 or 25 mm. Now, if you go back to our understanding, if I have a 15 mm SOD, my layer is going to get melted more, previously deposited layer. If I have 20 or 25 mm, my deposition will be higher compared to 15 mm. Now, if you go by that logic, what will happen? The peak in your waviness will get melted, the valley will get filled. Now, if you see, all that you are trying to do over here is just by changing the SOD, but the process physics behind what is happening by changing the SOD is very different. What are you changing? The laser material interaction length or the energy apportionment is what you are changing. So these are typically technical jargons that we use in additive manufacturing. So now if you see, all that you are doing for a layman is the SOD, but what is happening behind is something which is very important, which is actually selectively melting the peak and selectively filling the valley. Just one or two passes of such kinds will make your surface smooth, and you will be able to continue the deposition of 212 layers or whatever number of layers you want. You can keep depositing, and whenever you come across the waviness, all that you are supposed to do is adjust your SOD in such a way that it is above the focal point in case of peak, below the focal point in case of valley, so that peak can be melted, valley can be filled. This is an interesting study which we are now using in our large scale area additive manufacturing, where whenever we see such kind of undulations or any errors, we were able to repair them in an in situ way. Okay, now what happens if you do that? At the end of the day, we all want component, right? So now if you see, after all these efforts, what we were able to generate in this particular study, right? Now, why did we limit with rectangular walls? Is very simple, because all these properties of these materials, because you have to understand the way the conventional materials are made, the way the components out of additive manufacturing are made are very different. So their mechanical properties are different. So we need to test their mechanical properties. So that's the reason you are seeing blocks or the rectangular walls over here. I mean, like, to be frank, to make this 120 mm height wall over 100 mm width, it takes close to 4 to 5 hours, because in between we stop to take care of heat accumulation effects and other things, right? Now, within this, again, you have a couple of them, like this is overlapping tracks and overlaying layers. But in these two cases, what we have tried to do is only one bead over the other bead. We kept on depositing. There are no overlapping tracks, because again, the kind of mechanical properties this guy shows and the kind of mechanical properties this guy shows are extremely different. I did not touch their mechanical behavior, because the next aspect that comes to us is the mechanical behavior. Now, how do we verify? For us, when we talk about mechanical behavior, it's not just the stress strain curves. We look at the strain distribution. When you take a tensile specimen and when you do the stress strain curve, right? You get a stress strain curve, and based on that, yield strength and other thing. But during the tensile stress, have you ever thought of measuring what is the strain over here, what is the strain over here, what is the strain over here, what is the strain over here? Is very important in additive manufacturing, because this is a layer by layer manufacturing process. layer by layer manufacturing process. So that we will try to look from the perspective of something called as DIC, that is digital image correlation, where we will get the strain distribution over entire component length. Now, this is where we will try to, now we are trying to automate the process, where all that you can do is attach a displacement sensor back, because ultimate idea over here is to make the process what you say smart. Just give me 1 minute. Step. Yeah. Sorry. Yeah. So now, one is, when should your what you call so-called the sensor respond, or when should your power be adjusted, or when should be your SOD should be adjusted. So someone should tell the equipment or the machine that, okay, you are now supposed to change your course or the standoff distance. Again, how do you make it smart? All that happens by a displacement sensor. What this displacement sensor does, you have to also think of a control system which is stable, right? Now, what this sensor does essentially is, it will keep scanning for each layer. Just, it's not an what you call, it's an in situ process. As the deposition is going on, it's measuring what is the kind of waviness it is encountering. Now, all that it does is, it does not store entire data. Once one layer entire data is temporarily stored in its file, it will identify the lowest point, it will identify the highest point. That will tell you what is the highest difference between the peak and the valley. Now we will set a control limit to it. If the peak to valley distance crosses a particular value, then you change the SOD in such a way that the distance between the peak and the nozzle tip is lower compared to the focal point, and the distance between the what you call nozzle tip and the valley is high, such a way that more amount of deposition takes place. So that way you will be able to create an entire control system, because again, like I'm saying, when these machines go into industry, the human intervention should be as minimum as possible. Not just that, even in our labs also, we would like to have, to the extent possible, the best component deposition, because that will allow us to save the material, men and machine hours. Okay, so again, this allows you to make the process more what you call smart. Okay, so now if you see, the essential idea here of introducing this particular method is that what kind of sensors can you can integrate. Now, can this displacement sensor only talk about waviness in additive manufacturing? No, absolutely no. It can talk about surface roughness in your machining process. So based on the surface roughness, it can tell about your tool life condition. Is it just that? No, it can be used in cladding. Now again, if you go back and look at your IR parameters, is it that it is only used in additive manufacturing? No, it can be used in casting, it can be used in welding, it can be used in machining, anywhere where heat is involved, which acts as a signature. So the essential idea again about introducing all these things, though of course this FDP is more based on additive manufacturing, so we have selected additive manufacturing domain, and within that we are trying to show how to make it smart. But it can be used in any kind of manufacturing processes where heat is involved, where the surface quality is of important factor. Okay, so considering the time, this is where I will stop, because again the next topic will be much bigger, right? And if you have any doubts, we can interact regarding this process. Yes. Yes, Srihar here.
No, sir, I was about to announce that
Yes.
participants can raise.
Yeah, sure.
Participants, please unmute yourself and raise your questions, please.
Yes, Dr. Satyanarayan.
Yes, sir. See, actually, these days, of course, those two things may be entirely different, but just for the sake of thing I want to ask you. These days, titanium alloy castings are also made actually, like impeller, which you has shown it by,
Yes.
I mean, the R&D stage.
Yes.
That's having the vacuum induction melting and the casting chamber and all that. So here, why not we have a vacuum chamber so that some of the problems associated with the oxidation may be solved. What do you?
Yes. Yeah. So we see for these reactive materials, we typically use vacuum chamber. Again, there are, the domain of applications are entirely different. Now, when we talk about titanium and titanium-based alloys, especially for implants and other things, we do it in two methods. One is a controlled atmosphere. That is, in powder bed fusion process, you take care of the ppm level of the oxygen. If you can control the ppm level of oxygen, you will be able to deposit a component without much oxidation. That is one. You need not go into the vacuum. The other one is where you use the electron beam. If you look at electron beam based additive manufacturing process, there the entire process is done in vacuum only, which we are going to add to our systems soon, where you will see a vacuum like this electron beam based additive manufacturing process, which will be done under vacuum. Especially the purpose of procurement of that mission through project is for processing the reactive materials. So you are absolutely correct. Yes, we do work on vacuum based additive manufacturing process as well. That is feasible.
Thank you, sir.
Any other questions? Yeah, since there are no questions.
Yeah, Apparo sir, maybe you can summarize, please.
Okay. Thank you, sir. Thank you, sir, for providing immense knowledge to all the participants of ATAL FDP in the area of additive manufacturing. Dr. Mogola Gopinath Garu delivered an insightful presentation on various advanced concepts related to additive manufacturing, shedding light on its transformative role in modern industries. Gopinath Garu started with insightful side on laser directed energy deposition, laser area, laser manufacturing, heat accumulation effect in additive manufacturing, etc. He emphasized the intricate process, materials, and technological advancements that are revolutionizing production and manufacturing strategies. The discussion delivered into cutting-edge topics such as the integration of diverse materials and precision-driven nature of additive manufacturing technologies. His detailed explanations underscored the growing importance of this technology in optimizing manufacturing process, enhancing product designs, and driving sustainability initiatives. He emphasized the heat accumulation effect in additive manufacturing, how heat distribution varies based on the manufacturing conditions and the number of layers being deposited, and how heat management affects the quality and quality of the additive manufacturing process. He explained well the predicting and controlling waviness in additive manufacturing, and also real-time monitoring in laser directed energy deposition. The variation of process parameters to control the waviness is also explained very well, and the variation of process parameters on thick and thick wall deposition, and the influence of standoff distance on deposition quality. Uh, Last, I on behalf of all the participants, we sincerely thank Dr. Mogola Gopinath Garu for his engaging and informative session, which provided valuable perspectives and deepened our understanding of this critical and ever-growing smart manufacturing area. Thank you, sir. Thank you very much, sir.
Yeah, thank you, Apparo Garu. Sir, Gopinath Garu, maybe I just now noticed there is a query in the messages box by Dr. Sivasankar Raj Garu. Like he is asking, good evening, sir. During start and stop, deposition rate differs. How to control run? Please explain.
Okay. So this comes from the, he is correct. During the stop and the start, there is an additional deposition. That happens because you look at any kinematic system. Now, when you talk about a kinematic system and you set a velocity of, let us say, 1000 mm per minute, and the moment you press the start button, and if you are assuming that it is reaching 1000 mm per minute, then its acceleration is infinity. Now, that is not possible. So it takes from 0 to 1000 mm per minute, it reaches over a period of time which may be in few milliseconds. It can be 2-3 milliseconds. But in this 2-3 milliseconds, your deposition is going, which is going to give an additional deposition at the start, as well as at the end when it tries to take a turn. First, it has to decelerate, reach to the velocity 0, and then again it has to accelerate while it is returning to reach to the set velocity. So this acceleration and deceleration will actually create an additional deposition there. Now, is there any way to make it 0? No. Then what are we doing? While the deposition happens, we never keep the start and end point same. Rather, we randomize it. One, you can keep it systematically that every time this start and stop point changes by certain value, or you completely randomize it. The moment you randomize this start and start point, it will become uniform across. And then you won't be able to see start and end effects in any additively manufactured components. This is a well-established technique. Yes. I hope I have answered Dr. Shivashankar Gar's question. Yes.
Yeah, like maybe his bandwidth is a bit low, but he gave the thumbs up, sir. Yeah,
Okay.
thanks a lot, sir. Thanks on behalf of the organizers. I thank you, and you are always supportive to our college and department. Thanks a lot, sir. Good
Yeah,
night.
thank you. Thanks a lot for the invitation. Okay.
Yes.
Thank you.
Participants are requested to give their feedback for today's session, and you can leave. And tomorrow is the last day, and the session start at 2 p.m. Please make a note of that. There are 3 sessions followed by the feedback, online test, as well as the valedictory. Please join us. Thanks a lot. Good night.